Good morning. So far we've talked about limits that have an endpoint, right? We evaluate a limit and we get some sort of number of 1/2, -1/8, 10 million, something like that. But there is a such thing as an infinite limit. And that's when we go to take a limit and the answers we get just go bigger and bigger and bigger, and there's nothing we can do about it. So let's go ahead and start off with a definition. Suppose f, a function, is defined for all x near a point A. If f of x grows arbitrarily large for all x sufficiently close to A, we write the following and we say that the limit of f of x as x approaches A is infinity. So what exactly does that mean? Let's go ahead and look at an example really quick. So in this example, I've gone ahead and I've drawn the graph of the function f of x equals 1 over x squared. We're familiar with x squared as a graph. We just get a U-shaped centered at 0, 0. But now we're interested in 1 divided by x squared. So as you can see, as we approach 0 from the left and right, our values just go up and up and up. As we approach 0 from the left and the right, our value goes greater and greater and greater, and there's not really anything we can do about it. So we've evaluated this graphically, and we can kind of believe that either side as we approach 0 is going towards positive infinity. But let's look at it numerically. So I've drawn a table here, and it's got x values and f of x values. And let's go ahead and plug in plus or minus 0.1. I say plus or minus here because it doesn't matter if we go from the left-hand side or the right-hand side. We can just plug in positive 0.1 or negative 0.1. So let's go ahead and plug in positive 0.1. F of 0.1 equals 1 divided by 0.1 squared. And that equals 100, which means our value here is 100. We can do the same thing for plus or minus 0.01, and we'll get out the value 10,000. And if we do the same thing for 0.001, we get out the value 1 million. So obviously, from the right or the left, as we get closer and closer to 0, we actually approach the value of infinity. And that's a pretty big concept. So go ahead and take a pause, and we'll start back on negative infinity. So just like we can have positive numbers, we can also have negative numbers. So if there's a positive infinity, there ought to be a negative infinity. So let's go ahead and start with the definition. If f of x is negative and grows arbitrarily large in magnitude, that means it gets closer and closer to negative infinity. For all x sufficiently close to A, we write the following, and we say that the limit of f of x as x approaches A is negative infinity. So let's go ahead and see what that looks like. Now, I have in a red box here that in both cases, the limit does not exist. Infinity is a concept and not a number. So writing that the limit goes to infinity says that it automatically doesn't exist. But that's different than if it didn't exist because your function went one direction from the left and another direction from the right. So let's go ahead and look at an example. So in this example, we want to analyze the following limits. We're interested in what happens as the limit of x over x squared minus 1 quantity squared goes from x approaches 1. So just like before, as we get closer and closer to positive 1, either from the left or the right, our function increases in value and it's unbounded. It's going to go towards positive infinity. So we write our infinity symbol, and we also know that that means that it does not exist. And just because mathematicians are lazy, I'm using my DNE shorthand one more time. But now let's see what happens as we approach -1 from the very same function. As I approach -1 from the left and from the right, my values are getting more and more negative. They're getting larger and larger, but those are still negative values. So down here is negative infinity. So we can write that the limit as x approaches -1 of our function equals negative infinity, which is the same thing as saying it does not exist. So we're interested in, well, you saw my red dashed lines, and we were interested in our graphs approaching positive or negative infinity. And those red lines that we had on our graph have a name, and they're called vertical asymptotes. It's a very difficult word to spell. It's a harder word to pronounce, but don't worry, it's okay if you goof it up. You'll get it eventually. And this is what happens when we say, if the limit as x approaches a of a function f of x approaches positive or negative infinity, or the right-hand limit or the left-hand limit approaches positive or negative infinity, we call the line where x equals a vertical asymptote of f. So what exactly does that look like? Here I've got another graph, and this is just a function I pulled out of a textbook, and we can see we've got dashed lines at -3 and we've got dashed lines at +1. Let me get out my pointer. We've got dashed lines at -3 and we've got dashed lines at +1. And when we go and we approach +1 from the right, it goes to positive infinity. And as we approach +1 from the left, it goes to positive infinity. So we know that the limit as x approaches 1 is positive infinity. But let's look at what happens at the vertical asymptote of -3. From the right, we go towards positive infinity, and from the left, we go towards negative infinity. Well, our limit on the left does not equal our limit on the right, and thus it does not exist. And this one just straight up does not exist. It doesn't go towards positive infinity. It doesn't go towards negative infinity. It just doesn't exist at all. Versus our limit as x approaches 1 equals infinity, but does not exist because it equals infinity. So those are some pretty big concepts. And that's going to be the end of this video. I'll let you guys sort of ruminate on it. And there's going to be homework assignments and homework 2 that are going to help you get a little bit more familiar with what's going on.